In this video, we will formally define the dual linear programming problem, and we will also see some of its basic properties. My target in this slide is to define the dual linear programming problem for any primal linear programming problem. And with this, I mean that in the primal we can have inequalities of any type, so of the form greater than or equal to, less than or equal to, and equal to. And we can also have any variable either free or non-negative or non-positive. If you look now at the primal, I have only written my objective function, min C transposed x, subject to a bunch of inequality constraints of the form greater than or equal to, and these are denoted by AI transposed x greater than or equal to bi for I in an index set M1. And let's say for now that all the variables are free. So for now, this primal problem doesn't have all the freedom that I want to obtain. But let's start with this special structure, and then step by step we're gonna add a different type of constraints over here and different types of variables that can be non-negative or non-positive down here. So why do I start with such a simpler primal linear programming problem? Well, that's because we've already seen how the dual looks like. In fact, we have seen that for every primal constraint of the form AI transpose x greater than or equal to bi, we need to introduce in the dual a variable pi which is greater than or equal to 0. On the other hand, for every free variable xj in the primal, we have a corresponding constraint in the dual of the form p transpose aj equal to cj. When we looked at the primal in standard form, instead, we looked at equality constraints and variables that are all greater than or equal to 0. For every equality constraint in the primal of the form AI transpose x equal to bi, we introduced a dual variable pi which was free. Moreover, for every non-negative variable xj in the primal, in the dual we had the inequality constraint p transpose aj less than or equal to cj. At this point, we still have to consider inequality constraints in the primal of the form less than or equal to, and variables in the primal that are non-positive. For every inequality constraint of the form less than or equal to in the primal, in the dual we introduce a non-positive variable. The reason we do this is intuitively clear. In fact, for the inequalities of the form greater than or equal to, we introduce non-negative variables so that if we multiply the inequality by the dual variable, the inequality remains of the form greater than or equal to. On the other hand, if the inequality is of the form less than or equal to, we want to multiply it by a dual variable that is negative, because then the inequality sign flips, and so these two types of inequalities can be summed together, and we still obtain an inequality of the form greater than or equal to. Finally, note that the inequalities of the form less than or equal to in the primal, which we just discussed, behave in a symmetric way with respect to the inequalities of the form greater than or equal to. In fact, the inequalities of the form greater than or equal to give rise to non-negative variables, while the inequalities of the form less than or equal to give rise to non-positive variables. The last thing we need to discuss in the definition of the dual are the non-positive variables in the primal. These variables behave symmetrically to the non-negative variables. So while the non-negative variables gave rise to inequalities of the form less than or equal to in the dual, the non-positive variables give rise in the dual to inequality constraints of the form greater than or equal to. In particular, for every non-positive variable xj in the primal, in the dual we have the constraint p transposed aj greater than or equal to cj. At this point, our definition of the dual problem is complete. Essentially, for every primal linear programming problem in the left, the corresponding dual linear programming problem is the problem in the right. You see that at this point you can pick any linear programming problem with inequalities of any possible form. You then subdivide your inequalities based on which form they are, so either greater than or equal to, or less than or equal to, or equal to, and then you subdivide your variables into the non-negative, the non-positive, and the free ones. Once you've done that, you just need to follow the instructions of the definition and you can write down the dual. In particular, for every constraint of the primal problem that is not a signed constraint on a variable, In the dual, we introduce a corresponding variable. The sign constraint on this dual variable is determined by the type of original constraint that we had in the primal. If the inequality constraint was the form greater than or equal to, then in the dual we have non-negative variable. If the sign constraint is of the form less than or equal to, then in the dual we have a non-positive variable, and if the primal constraint was an equality constraint, then the dual variable is free. Then for every variable in the primal we have a corresponding dual constraint. The left-hand side of all these constraints is always P transpose Aj for variable xj, and the right-hand side is always Cj. What changes though is the type of inequality. If the primal variable is non-negative, then the dual constraint is of the form less than or equal to. If the primal variable is non-positive, then the dual constraint is of the form greater than or equal to. Finally, if the primal variable is free, then the dual constraint is an equality constraint. In order to easily memorize how to construct a dual linear programming problem, we write down this table. The left part of this table represents the primal, while the right part represents the dual. In the primal we minimize, while in the dual we maximize. For every constraint of the primal, we have a corresponding dual variable. And the inequality signs between these constraints and these variables are somewhat maintained. If in the primal constraint I had a greater than or equal to, then the dual variable will be non-negative. If in the primal constraint I have an inequality of the type less than or equal to, then the dual variable is non-positive. Vice versa, for every variable in the primal I have a corresponding dual constraint. And in this second case, the signs between the variables of the primal and the constraints of the dual are somewhat switched. In fact, for every non-negative variable in the primal, I have an inequality constraint in the dual of the form less than or equal to. Vice versa, for every non-positive variable in the primal, I have an inequality constraint in the dual of the form greater than or equal to. At this point, we know how to construct the dual linear programming problem to any primal linear programming problem of minimization form. So what if instead you have a primal linear programming problem where you wish to maximize your objective function? Well, in this case, we know how to transform any maximization problem into a minimization problem. So what you should do is first transform the maximization problem into a minimization problem, and then construct the dual linear programming problem. So to avoid confusion between primal and dual, we will always have our primal linear programming problem that is in minimization form, while the dual will be in maximization form. Normally in the primal we refer to the objective function as a cost that is minimized. In the dual we will still talk in terms of costs. So for us the dual objective function is a cost that is being maximized. Let's immediately see an example of a specific primal linear programming problem and the corresponding dual. Here on the left we have our primal where we're minimizing x1 plus 2x2 plus 3x3. Then we have one equality constraint, one inequality constraint of the form greater than or equal to, and one inequality constraint of the form less than or equal to. This problem has three variables. One of them is non-negative, one is non-positive, and one is free. Now the dual is shown here on the right. In the dual we're maximizing, and since in the primal problem we have three constraints that are not sign constraints on the variables, we're going to have three dual variables. So P1 will be associated with the first, P2 with the second, and P3 with the third constraint from the primal. The right-hand sides of these three constraints give us the coefficients in the dual objective function. Such an objective function then is 5p1 plus 6p2 plus 4p3. Next, let's look at the sign constraints of the dual variables. The first constraint is an equality constraint, so p1 is free. The second is an inequality constraint of the form greater than or equal to, so p2 is non-negative. And the third is an inequality constraint of the form less than or equal to, so p3 will be non-positive. Next, we look at the sign constraints on the variables in the primal. The first one is non-negative, So the corresponding inequality will be of the form less than or equal to. The second one is non-positive, and the corresponding constraint will be of the form greater than or equal to. The third one is free, and the corresponding constraint will be an equality constraint. But what about the coefficients of the dual constraints? The first dual constraint corresponds to the variable x1. So we need to look at the coefficients of x1 in the primal constraints. The coefficients are -1, 2, and 0. So we have minus 1 p1 plus 2 p2 plus 0 p3. The right-hand side of the inequality comes from the coefficient of x1 in the objective function of the primal, so it is a 1. Similarly, the second constraint of the dual corresponds to the variable x2 in the primal. So we look at the coefficients of x2 in the primal constraints. We have a +3, a -1, and a 0. Correspondingly, we have 3p1 minus 1p2 plus 0p3. And the right-hand side 2 comes from the coefficient 2 of x2 in the objective function of the primal. Finally, let's look at the third constraint of the dual. This corresponds to the variable x3 of the primal, and its coefficients in the primal constraints are 0, +3, and 1. We obtain 0 p1 plus 3 p2 plus 1 p3 equal to 3, because 3 is the coefficient of x3 in the primal objective function. At this point, I want to show you something quite interesting. What I want to do is to write down the dual of my dual. But my dual is a maximization problem, so I need to transform it into a minimization problem. We know that the max of a function is equal to minus the minimum of minus that function. Accordingly, I can change my objective function from this one to this one. This is not the only modification that I performed in my dual from the previous slide. The other difference is that I multiplied all the last three constraints by -1. Of course, I don't change anything if I do so, and so I obtain an equivalent problem. The reason I am multiplying by -1 these three constraints is really unclear at the moment, but let's just run with it. Now I am in a position to write down the dual of my dual, so let's write it on the left. I'm not going to discuss once again how you obtain this dual problem, and I leave it to you as an exercise. Now in my dual of the dual, I multiply my first three constraints by -1. Again, this transformation is out of the hat, but in any case, I will obtain clearly an equivalent problem. Furthermore, I transform this maximization problem into a minimization problem, again with the same trick. If we perform these operations, we obtain the problem written here, which is therefore equivalent to the dual of the dual that we obtained previously. Surprise! This is exactly the primal problem we started from. Of course, this is not just a coincidence. In fact, the primal problem that we started from in our previous example had all the ingredients of a general linear programming problem. Namely, it had one inequality per type and one variable per type. This suggests that the observation that we reached at the end of the example should hold for general linear programming problem. And this is in fact true and is stated here in theorem 4.1. If we transform the dual into an equivalent minimization problem and then form its dual, we obtain a problem equivalent to the original problem. This is the first interesting result that we see about duality. And a compact statement that is often used to remember this theorem is the dual of the dual is the primal. I leave the proof of theorem 4.1 as an exercise for you. In order to write down this proof, you have to follow the same exact steps that we performed in our example. Essentially, you only need to substitute the specific numbers with abstract symbols. The next interesting result about duality that we're gonna see essentially says that the duals of equivalent problems are equivalent. What does this exactly mean? Well, you see, there are several different ways in which we can manipulate our primal linear programming problem in order to obtain an equivalent one. And we've seen several already. For example, you could introduce slack variables to turn inequality constraints into equality constraints. Or you can replace a single free variable with a difference of two non-negative variables. By making these changes in the primal, and then following the definition of dual problem, we will obtain, of course, dual linear programming problems that look quite different. Nevertheless, we will see that the corresponding dual problems will also be equivalent. Let's immediately see an example of this type of transformations. Let's look at the primal problem written here. We're minimizing C transpose X subject to AX greater than or equal to B and X free. If we write down the dual following the definition, we obtain the problem of maximizing P transpose B subject to P greater than or equal to 0 and P transpose A equal to C transpose. So now let's manipulate the primal problem by adding surplus variables. Instead of having AX greater than or equal to B, I will have AX minus S equal to B. And I'm adding the non-negativity constraints on the surplus variables. The objective function remains the same, so it's C transpose X plus 0 transpose S. Now we know that this linear programming problem is equivalent to our original primal. If we write down the dual of this new primal problem, we obtain maximize P transpose B subject to P free, P transpose A equal to C transposed, and minus P less than or equal to 0. As you can see, this dual is equivalent to the original dual. Essentially, the only difference is that while in the first dual we had P non-negative, in the second dual we have that minus P is non-positive. But these constraints are obviously equivalent because one is obtained from the other one by multiplying by minus 1. Now let's make a different change to our original primal linear programming problem. We replace the x vector of variables with the difference of non-negative variables. So in our new primal, we minimize C transposed x plus minus C transposed x minus. The constraints are ax plus minus ax minus greater than or equal to b, and x plus and x minus non-negative. We know very well that this new primal problem is equivalent to the original primal problem. If we now write the dual to this linear programming problem, we obtain the problem of maximizing P transpose B subject to P greater than or equal to 0, P transpose A less than or equal to C transposed, and minus P transpose A less than or equal to minus C transposed. If we multiply by minus 1 this last constraint, we obtain P transpose A greater than or equal to C transposed. And together with the previous constraint, it tells me that P transpose A is equal to C transpose. So once again, also our third dual problem is equivalent to our first dual problem. In this example, I didn't spend time explaining you how these dual linear programming problems are obtained from the primal, but you should make sure that you're able to construct them. Everything you need to do is follow our definition of dual. Furthermore, in order to fully understand the material, you should make sure that you completely understand why the problems that I said that are equivalent are indeed equivalent. In the next example, we're going to see how a different manipulation to the primal problem also leads to equivalent dual problems. In particular, we look at the primal problem in standard form, and we assume that one of the equality constraints is redundant. We will then see that the original dual problem is equivalent to the dual problem obtained after dropping such a redundant equality constraint. Here we have on the left our primal linear programming problem in standard form. On the right, we have the corresponding dual problem. We assume that the last equality constraint in the primal problem is redundant. We know that in this case, such an equality constraint can be eliminated from the problem in order to obtain an equivalent problem. So what does it mean that the last equality constraint is redundant? It means that it can be written as a linear combination of the other equality constraints. As always, we denote by AM the last row of the constraint matrix A. Then the vector AM can be written as a linear combination of the other rows. So we have AM equal to the sum of gamma I AI for I that ranges from 1 to m minus 1. Here, the gamma I are scalars. Correspondingly, the right-hand side of the last equality constraint, which is Bm, can be written as the same linear combination of the right-hand sides of the first m-1 equality constraints. Now let's write down the dual cost P transpose B. We break down the scalar product as the sum of its components, and we isolate its last component. So this is the sum for I that goes from 1 until m-1 of Pi Bi plus Pm Bm. Now we replace Bm using the equality that we just derived. Once we have replaced Bm with the sum of the gamma I Bi, we can write down our dual cost as the sum for I that goes from 1 to m-1 of Bi times Pi plus gamma I Pm. We have now written the dual cost P transpose B in a form that will be useful to us in just a moment. Now let's do the same thing for P transposed A. We write down P transposed A by expanding the components of P and isolating once again the last component. So this is equal to the sum for I that goes from 1 to m-1 of Pi AI transposed plus Pm Am transposed. Once again, we can replace this Am with the sum that we derived earlier on. Once we have done that, we can write P transposed A as the sum for I that goes from 1 to m-1 of Pi plus gamma I Pm AI transposed. So let me recap. We have obtained this formula for P transpose B and this formula for P transposed A. As you can see, these two formulas have a part in common, namely Pi plus gamma I Pm. The idea now is to replace this quantity with a new variable that we can call, for example, Qi. So let Qi be equal to Pi plus gamma I Pm for every I from 1 to m-1. At this point, the dual problem takes the following form. We maximize the sum of the Qi Bi for I that goes from 1 to m-1, subject to the sum of Qi AI transposed less than or equal than C transposed. It's a good exercise for you to check that this new problem that we've written here is in fact equivalent to the original dual problem. Now, why are we interested in this alternative form of the dual problem? Well, this is because if we had first eliminated the redundant constraint and then written the dual, then we would have obtained exactly this dual. So we have shown that removing a redundant constraint from a primal problem in standard form leads to an equivalent dual problem. The next theorem precisely tells us what type of operations you can perform to the primal problem and still obtain an equivalent dual problem. In particular, the last two examples that we have seen are implied by this theorem. But this theorem is actually more general. Suppose that you have a primal linear programming problem pi1 and you transform it to another linear programming problem pi2 with a sequence of transformations of the following three types. Type A is replace a free variable with a difference of two non-negative variables. Type B is replace an inequality constraint by an equality constraint involving a non-negative slack variable. And finally, type C is if some row of the matrix A in a feasible standard form problem is a linear combination of the other rows, eliminate the corresponding equality constraint. Then this theorem says that the duals of pi1 and pi2 are equivalent. Once again, in the previous two examples, we have proven part of this theorem. I leave it to you to figure out also the remaining parts of the proof. And this concludes our video on the dual linear programming problem. In the next video, we will study the duality theorem.